So welcome to the next TCS Plus talk. We are very excited to have Yichuan Wang speaking at the seminar today. So he's a first-year PhD student at UC Berkeley, co-advised by Liji and Avishai. And he has already done impressive work in different areas of complexity theory. And today we'll be hearing about their joint work on super-quadratic lower bounds for depth 2 linear threshold circuits. We are very excited to have you and to you.
Okay, thanks for the introduction. Okay, so hi everyone, I'm Yichuan, and today I'm going to present our work on special circular lower bounds. So this is a joint work with DJ and Avishai. Okay, so this is today's plan. So we will first talk about some history and the backgrounds in TC0 circular lower bounds, and then I will present some of the most important ideas behind our new proof. Okay, so let's first start with the problem setting. So the definition of TC0 circuits. So TC0 circuits, they are polynomial sized constant depth circuits with linear threshold gates and also free NOT gates. Okay, so and here I need to define what is a linear threshold gate. And we are interested in those two types of gates. So they are the majority gate and the real weighted threshold gate. The majority gate is just a gate that computes the majority function. And the threshold gate, so it is computing a more general linear sum. Let's say there are weights W1 to Wn, and what we compute is we take an input string and we output this, and we compute this linear sum of the input bits and test whether it is larger than some threshold value. And you can think this majority gate is just a real weighted threshold gate, but with weights of B1. And for those two type of gates, actually we have this relation. So one layer of threshold gate, it can be simulated by two layers of majority gates. So this means the TC0 circuit defined by those two type of gates, they actually give the same definition. And in fact, there is a more general relation. So for any constant k layers of threshold gates can be simulated by k+1 layers of majority gates. And what's the relation of TC0 and the other circuit classes? So it lies between ECCC0 and NC1. So ECCC0 is maybe the largest circuit class, one of the largest circuit class. We have some non-trivial circuit lower bounds. So from TC0, we don't have better lower bounds than T/poly. And the big open problem of TC0 circuit lower bound is prove. So can we prove Nx is not in TC0, or even e to the np is not in TC0? So these are very large complexity classes. We still don't know how to prove the lower bounds. So although what we believe is TC0 is very weak, so we even believe that P is not in TC0. Okay, so now because people cannot just prove those general TC0 circuit lower bounds, so maybe we can do it step by step. Let's say, can we move from, let's say, can we prove first lower bounds like for depth 1 TC0 circuits, and then depth 2 TC0 circuits, and then depth 3, depth 4. So can we do this and finally move to arbitrarily constant depths? Okay, so now let's look at the depth 2 TC0 circuits. Okay, so because there are two types of gates, majority of threshold, so we can have those four types of depth 2 circuits. Let's say by choosing, so what type of gate is allowed in each layer. So we have majority of majority, majority of threshold, threshold of majority, threshold of threshold. And here, like threshold of majority, it just means, so for the top layer, the top gate, it can be a threshold gate, but the bottom gates, they are all majority gates. Okay, let's see what we already know about those four type of depth 2 circuits. Okay, so for the first three types, so we already know some very strong lower bounds. The inner product function cannot be computed by those circuits. So here the inner product function is just the inner product over F2. So you are given an input bits, and you interpret them as two over two length vectors over F2, and you compute their inner product. So we already know lower bounds against this very explicit function, and they were proved over 20 years ago or 30 years ago. And then these proofs were using some traditional circular lower bound techniques. Okay, but for the last circuit, let's say 2 layers of threshold. So even for the very strong complexity class E to the NP, we don't yet have a lower bound. So that's where the lower bound stops, and this is actually feels very embarrassing because even only depth 2, we don't have a good lower bound.
So I have a question. For all the other depth 2 circuits, are the lower bounds super polynomial? Like the inner product lower bounds, are they super polynomial?
Yes, super polynomial. So polynomial size circuits cannot compute those functions.
I have a question. Is inner product in threshold of threshold?
That's a good question. Let me think about it. Okay, so inner product, so trivially it is a XOR of and. Okay, so XOR, you can do it in threshold of threshold. So it is of course in depth 3 circuits, but depth 2. Okay, so I haven't think about it actually. Okay, maybe you can talk it later.
Sure, that's fine. Thanks.
Yeah. Okay. So now let's see. So how people today are trying to tackle this threshold circuit lower bound. Okay. So actually, so how people are tackling arbitrary general circuit lower bounds. So in 2011, so Ryan Williams invented this new paradigm in proving circuit lower bounds. So it's called the algorithmic method. So it says that so if you have non-trivial circuit analysis algorithms, then it implies circuit lower bounds. Okay, so let me tell you what does it mean. So for circuit analysis algorithms, so today we will consider the problem called CAP, so which is circuit acceptance probability problem. So for this problem, the input is now a circuit. And then what we need to compute is, so this circuit, it has a truth table of size d to the n. And then what we need to do is to estimate the fraction of ones in this truth table. And the typical setting is we allow a small O of 1 error. Okay, and by non-trivial algorithm, it means so an algorithm for computing this cap that runs in deterministic 2 to the n, slightly less than 2 to the n time. And here we remark that the trivial running time, let's say just enumerate over all input strings, it is 2 to the n times polynomial of n. So non-trivial is you need to make the running time less than 2 to the n. And Ryan proves that if we have a non-trivial ECC0 cap algorithm, then we have the circular lower bound and X is not in ECC0. And Williams also designed a cap algorithm for ECC0 circuits without any assumption, the unconditional algorithm. So it implies an unconditional circular lower bound. Okay, so then what about for our threshold of threshold circuits? So Williams reduction actually works for any good, maybe with some good closure property, circuit classes with good closure properties, they all work. Let's say for threshold of threshold circuits. So if you have a cap algorithm for XOR of 2 of threshold circuits, then we have the circuit lower bound. X is not in threshold of threshold. And here, this XOR of 2 is just means so the top gate is XOR of 2 subcircuits. So you can think it is an XOR of 2 threshold of threshold circuits. Yeah, so here we have a extra XOR at the top. And in fact, for the ACC0 circuit, this XOR is just absorbed by ACC0. Yeah, so, and here, this implication is just almost the same as William's original proof, but what we currently don't know is we don't have an algorithm for this threshold circuit. So in fact, so how people today are trying to tackle this threshold circuit lower bound is just let's try, can we design some non-trivial algorithms for threshold circuits? So this is what people are doing today. Okay, so and again, so because people cannot just directly design an algorithm for any polynomial size threshold circuits, so maybe we can also try to do something simpler. So let's say, can we first do some linear size algorithm, and then can we do n square size algorithm, and then can we move on to n third, n fourth, and finally to arbitrary polynomial size circuits.
So there's a question in the chat. I thought Ryan's result starts from next in ACC0 to get the non-trivial ACC0 cap algorithm, and then this is a contradiction.
Okay, so good question. So this is how the proof was written. So what do you guys think the general relation is? Okay, so logically they are equivalent. So if you have an algorithm, then it implies a circuit lower bound. And when you write the proof, you just write something like, if you both have this algorithm and you have this X in ACC0, then they together you get a contradiction.
Right. Yeah, thanks for the answer. I was just clarifying that we don't have an unconditional ACC0 cap algorithm, right? Like,
No, so this is something we already know. So we can design an unconditional ACC0 cap algorithm. It's just by something. You first do some circuit transformation, and then the final step is something like you do a fast matrix multiplication.
I see. Okay. Is there a reference for that? Because, like you said, this is not the presentation that Williams used, if I understand correctly.
I think it's just Williams' original ACC0 papers. Also, you mean
Okay, I'll take a look. Okay, thanks.
Okay, let's continue. So yeah, so if we are trying to do something like we first do linear size algorithm and square size algorithm and a third and blah blah blah. So actually, so if we care the exponent in this polynomial size, so for any constant alpha, so if we only have a algorithm for an alpha size XOR of threshold, so it can actually implies that e to the np is not in n to the alpha size threshold. Okay, so and there is a small loss that it is not for x but for e to the np. And okay, so actually for this, so it is implication in the second line, so it only works for general polynomial size threshold circuit. So maybe if we have a threshold algorithm for n to the 100, then we only get a lower bound for n to the 10 size. But this third line tells us that we can do this for those fine-grained size circuits. Okay, so now we are ready to present what is our result. So let's first see what are the previous results. So previously, so for explicit functions in P, we know that they cannot be computed by into the 1.5 size threshold circuits. And if we use the algorithmic method, then we have that e to the n_p cannot be computed by n square size threshold circuit. And this e to the n_p lower bound is just by designing a n square size algorithm. Okay, so and our result is, so for this algorithmic lower bound, so we improve this from n squared to n to the 2.5. So we prove that e to the n_p cannot be computed by n to the 2.5 minus epsilon size threshold circuit. And our proof is just by designing a new algorithm that works for cap of n to the 2.5 size threshold circuits. Okay, so this is the background part of today's talk. So does anyone have more questions?
No questions.
Okay, good. Let's continue. Okay, so now let's move on to the technical part. So I will present some ideas behind our proof. Okay, so the first idea is called, let's combine random restriction in our algorithmic method. Okay, so let me first tell you, so what is the general framework to design those circuit analysis algorithms? So for the circuit we want to analyze, so it has a less n input. So the standard step is we partition this input into two parts. So this short prefix has length into the epsilon over 10, and the longer suffix, it has length minus into the epsilon over 10. So this is the standard step. And then what we do is that for this circuit truth table, so we put them into this 2 to the n to the epsilon over 10 by 2 to the n minus n to the epsilon over 10 table. So the row index is just corresponding to its prefix, and the column index is just corresponding to its suffix. And what our cap algorithm do is that, so we actually can compute a cap for all columns as an intermediate step. So this means, so the cap algorithm asks us to approximate the fraction of ones in this whole truth table. But actually we can output the fraction of ones, so an estimate of fraction of ones of each column as an intermediate step. And then for the cap of the whole truth table, we can just add the fraction of each column together and then get the cap of the whole truth table. Okay, so then how to combine random restrictions. Okay, so now I have written this in the title, so maybe it looks very natural to how to combine with random restriction. So in this prefix suffix partition, let's just view the prefix as free variables and the suffix as the fixed variables in a random restriction. So now let's see. So wait. So now in each column, so the row index can be some arbitrary thing. So it is corresponding to the free variables in the prefix. They can be arbitrary 0, 1, but its column index is some fixed value. So it is corresponding to this long suffix. It is a fixed 0, 1 string. And so this means, so each column is a restriction. And in terms of random, so you can think when you pick a random column, so then it just means by setting the suffix to be a random fixed 0, 1 string. And in fact, so in this prefix suffix partition, you also don't need to strictly partition it as this prefix and suffix. So you can choose a random into the epsilon over 10 subset to be the free part. Okay, so now let's see, so what's the guarantee of random restriction when we apply random restrictions to linear threshold gates? So and we recall that, so today, so the random restriction we consider, so we need a fixed number of free variables. So let's say we let k be into the epsilon over 10. So we always choose k variables to be free variables, and each remaining bit is set to be 0 or 1 randomly. So then the guarantee on threshold gate is that, so after we apply a random restriction, let's say now most of the bits are fixed. So then a threshold gate remains non-constant with probability approximately k over square root n. So because k is very small, so you can think it's just approximately 1 over square root n. And let's see the proof. Okay, so I'm not going to show the complete proof, so I'm only going to show a core example. So what if we are simplifying a majority gate? Okay, so after we apply the random restriction, so if this gate is still non-constant, then we can say that the number of zeros and ones in the fixed variables, so they cannot differ too much. So because if over the fixed 0 and 1, so they already differ too much, then without looking at the free bits, you can already say its output is 0 or 1. So you don't even need to look at the remaining bits. Yeah, so but we can actually show that the probability that the number of fixed ones and fixed zeros bounded by k, so this probability is not so large. So because for any fixed number of fixed ones, so its probability is at most 1 over square root n, so by some standard binomial coefficient estimation. So then for all k possible values of number of fixed ones and number of fixed zeros, so the total probability is not more than k over square root n.
So I had a clarification question. The goal is to compute the probability that the answer is 1 or 0 completely, or like up to an error.
Okay, so let's go. Okay, so today we will just focusing on, so the error for this cap is plus minus little of n.
Little of 1. Okay.
Okay, and so here we are just talking about how many threshold gates simplifies when we
Yeah.
apply a random restriction. So no, we are not computing this cap. So we are just trying to simplify this circuit.
Yeah.
Okay, so now let's see. So we have this guarantee on threshold gates random restriction. So now let's see how to combine it in the circuit analysis algorithm framework. Okay, so we have this into the 2.5 minus epsilon threshold circuit, and let's put it to table like this, and then so each column, so a random column is just a random restriction. So what you can say is that, so now most of the columns, they are simplified to approximately n squared size circuits. So you can think, so after this random restriction, so on average, only 1 over square root n many gates they survive. So you do some Markov inequality, you can prove that. So okay, so first, on average, each column simplifies to n squared size, and then by some Markov inequality, you can show that. So most columns simplifies to n squared size. Okay, so then what you can expect to do is that something like, so previously we already have a n squared size algorithm. So now here we already have simplified most of the columns to n squared size. So can we just apply the previous n squared size algorithm? But here the problem is in this n0 2.5 setting, so the n squared size circuit we get on each column, so there are different circuits. But the previous algorithm only guarantees that if they are the same n squared size circuit, then I can compute everything together with some non-trivial algorithm. But here the circuits in each column, they are different ones. So you cannot just directly call the previous algorithm. So we need some other ideas to resolve this issue. Okay, so before moving on to the next idea, so we need to first look deeper into the previous square proof. So where does this square come from? So why it is not 1.5 or linear or something else? Why it is n squared? Okay, so why the previous result was n squared? So okay, so today I will skip a little bit details. So in fact, there's some reduction that we can reduce designing cap for threshold to cap of majority of threshold. Because I will not talk about how to do this today. So okay, so and there's one remark. So although previously we know majority of threshold lower bounds, so they were proven by some traditional methods, so not by the algorithm method. So the cap algorithm for majority of threshold or even majority of majority, so we don't have those algorithms. Okay, so this n squared actually comes from this key lemma proven by Alman and Williams in 2015. So the majority of n bits, it can be approximated by a square root n degree polynomial over f2. And here, this approximation, we use this pointwise approximation. So there is a distribution d over those square root degree polynomials, such that on any input string, for a random polynomial drawn from this distribution d, so px agrees with majority of x with very high probability. So this is the pointwise approximation. Okay, so and now we have this dilemma. So for an n squared size majority of threshold circuit, if we apply this lemma to the top majority gate with n square bits, okay, in fact, slightly less than n square bits, then we can replace it by a sublinear degree polynomial. And so for sublinear degree polynomial so for this circuit, so the top gate is a sublinear degree polynomial over f2, and the bottom gates are threshold gates. So for this kind of circuit, we have another cap algorithm. So we will also not talk about this today. So putting them together, they just get the previous n squared lower bound. Okay, so now I'm going to talk about the second idea. So it is called list approximation polynomials. So I will explain what does it mean later. So, but you can imagine this is something like the list decoding arithmetic code. Okay, so let's see what happens when we apply this polynomial approximation lemma to our n-to 2.5 size circuits. So we have this n-to 2.5 circuit, and previously we have done what we have done. So we write this truth table like this, and then on most columns it simplifies to n squared size. And for this n squared size, okay, so we replace the top majority gate by polynomials. Let's say now most columns becomes polynomial of threshold circuit, and this polynomial is a sublinear degree polynomial. Okay, so those polynomials, okay, so trivially they can be very different polynomials, but so the crucial observation in our proof is that we can actually construct those polynomials in a way to make there only into the 10 log n many different polynomials. Yeah, so this means so over those polynomials, let's say there are 2 to the n minus n to the epsilon or 10 many polynomials. So actually most of them appears a lot of times. So there are not so many different polynomials. And then what we can do is that, so we want to call the previous polynomial of threshold cap algorithm. So let's say what we do exactly is first for any different polynomial ti, so we invoke the previous polynomial of threshold cap algorithm on this ti of threshold. So and then so we get a very large truth table, let's say for each pi and each column. So what is the cap of pi of threshold on this column? And then in the second step of our algorithm, we can just do for each column. Let's look at which is specific pi is for this column, and then we look up the very large truth table to find the cap of pi of threshold for this column, and then we add them together and get the total cap result. Okay, so now and then I will present how to prove this crucial observation. So why they are only into the 10 log n many different polynomials. Okay, so and before presenting our proof, so we need to first.
So there's a clarification question. The threshold gates for distinct columns may be different. Is that true?
Okay, so that's a good question. Let me answer it. So the threshold gate, so why they may be different threshold gates? Because we apply a random restriction, and some threshold gate we just erase them. So then they may become different threshold gates. But here, let's view those threshold gates as the same threshold gates. So if this threshold gate is constant on this column, let's don't erase it. So let's just still put it there. Okay, so does that make sense? So they are still the same threshold gates.
Sorry, I think your audio cut out a little. I couldn't quite hear what you said about at the very end. What did you say? So that they are different for different columns, but then what?
Okay, so if you let's say if you erase all the constant threshold gates, then they may become different. But we don't do this. So if they are constant threshold gates, so let's still just keep it there.
Okay. Yeah.
So we don't erase the constant gates.
Yeah. Thank you.
So they are still the same ones, but just the inputs are from different subsets. Okay, so yeah. So let's see how this polynomial approximation theorem was proved. So in fact, here we are not just working on the majority function, but now we work on a more general function that computes the exact number of ones in this input string. So you are given an ambient input string, and you want to compute how many ones are there in this input string. So we need to because this is a multi-bit output function, so let's specify how do we encode this output. So we use this one-hot encoding. So which means there are n+1 many possible outputs. Then we just output a n+1 less n+1 vector, and then it means what the output is. So let's suppose the sum is little s. Then only the little s bit is 1, and the other bits are 0. So only one bit of this output vector is 1. And the theorem is saying that this one-hot sum function can be approximated by square root m degree polynomial. And we are still using this pointwise approximation. So there's a distribution d, but now it's over a n+1 tuple of square root m degree polynomials, such that on any input string for a random tuple of polynomials drawn from this distribution, so they agree with the one-hot sum result with very high probability. Okay, so now let's see how was it proved. So the proof is by doing an induction. So let's suppose now we are working on a sum of n bits. So we first sample a random m/2 subset of all those input bits. So you can think we sample half of the input bits. And then by induction hypothesis, so we have an approximation polynomial for the sum of those sampled half of bits. And also by concentration inequality. So when we, for this randomly sampled subset, so this partial sum on the sample bits, so it can actually give an approximation of the total sum. And the error is approximately plus minus square root of m. Okay, so then how do we make use of this sample sum? So the general idea is that the sum of the sample bits, so it gives a plus minus square root m approximation of the total sum. So and then in order to determine what's the exact value of this total sum over this square root m length candidate interval. So we can just do a interpolation polynomial on the total sum. So let's say we construct an interpolation polynomial here. And so if the total sum is exactly that value, then it outputs 1. And if it's other values in this square root m length interval, it outputs 0. And if it runs out of this square root m length interval, so it can be anything. So, but this only happens with very small probability, and let's just treat this part as the error. Okay, so and formally what we do is that, so let's say we want to compute the case bit of our one-hot output. So let's determine whether, so we want to know whether the total sum is exactly k. And what we do is that, so we first have this one-hot vector of the sampled bits. So let's look up which one is 1. And let's suppose this QS is 1, so which means so the sample sum is S. So then what we can do that is we have an estimate that with high probability, the total sum is now 2S plus minus square root n. And then we multiply it by our interpolation polynomial. So if the sum is exactly k, then we output 1. So, and if it is some value in 2s plus minus square root n other than k, then we output 0. And if it is not in this interval, we just output anything. And the probability that we move to this outside this interval, so this probability is very small, so we can just take it as the error. Okay, so the general idea of this proof is that, so just we first sample half of the input bits, and then from this sample bits, so we apply induction, and we get a plus minus square root m approximation of the total sum. And then for this remaining square root m error, so let's do a square root m degree interpolation polynomial to determine what's the exact value. Okay, so and what's the total cost of all induction rounds? So the total number of induction rounds we do is log n. So because each round we reduce to half of the input bits. And for the total degree of the polynomial, so in each round, so we can see, so we get an additional additive square root m degree. So the total degree is still total of square root m. Okay, so this was the proof of Alman and Williams. And next we will show, so how do we modify this proof so in our setting, so we can get not so many different polynomials. Okay, so let's see our changes. Okay, so let me first remind you, so what are the things we need? So now our circuit is into the 2.5 size circuit, and the top majority it has into the 2.5 inputs. Yeah, but now on each column, so the input is no longer, so the input fed to this top majority gate, so it is no longer arbitrary into the 2.5 length string. So now it is restricted to into the 2 minus epsilon over 2 dimensional subcube. So you can think on each column, so for the until 2.5, many special gates at the bottom. So only a square of them are still alive. So the other ones are already fixed. So this reduces the input space to this top majority gate to a square dimensional subcube. And then what we want to approximate this majority gate by a sublinear degree polynomial. Okay, so if those three are the only things we want, then you can just directly apply the Alman-Williams lemma, because the majority gate is now simplified to a majority gate of square bits. Yeah, but we also have our additional requirement. So we don't want to construct so many different polynomials. So we need that. So for different subcubes big X, we can only construct at most into the 10 log n different polynomials. Okay, so let's see how to do this. Okay, so let's recall. So in Alman-Williams' original proof, so the core step is we use this sampled partial sum to estimate this total sum. And let's see, so what does this become in our into 2.5 setting? So now okay, so we decompose this arrow more carefully. So because now the into 2.5 input bits, so there are some, so we have some free indexes, so corresponding to the threshold gates that are not fixed, and also those fixed indexes. So because most threshold gates, they are already fixed. Okay, so for those free indexes, so there are only a square many. So we can do a concentration bound. So the arrow from this free bits is only approximately sublinear. So this is good, because for this sublinear arrow, we can just handle this by a sublinear degree interpolation polynomial. Yeah, but for those fixed indexes, let's say they are corresponding to the fixed bottom threshold gates. So they are into the 2.5 many fixed indexes, then by a trivial concentration bound. So you can only get, so the arrow is into the 1.25 approximately. So that's bad, because we cannot handle this into the 1.25 arrow by an interpolation polynomial. So this would make the degree too large. But for those fixed bits, so there is another good thing about this. So you can actually see that, so the fixed bits, so they are already fixed for a given subcube big X. So this means this fixed arrow, so this arrow is also a fixed value for a given subcube big X. Okay, so then what we do, so let's just hard code this fixed arrow as an advice to our construction of the polynomial. And then, so when we estimate the total sum using the partial sum, we just manually shift this fixed arrow. Let's call it small a. So then we have handled this fixed arrow, and the only thing remains is the arrow from the free indices. So it can be plus minus sublinear of n. So it can be now handled by a interpolation polynomial. Yeah, so the core trick is now we hardcode this fixed arrow, and we just do this shifting manually. So because it is some fixed value for a given sub-Q big X. Okay, so now what's the important observation? So in fact, so in this construction of polynomials, so those values of small a's, so they are the only information that we need to know about this sub-cube X. So okay, so let's say for a sub-cube big X, so once those a values they are all given to us, then we no longer need other information about this sub-cube big X. So this means so everything we need to know about this sub-cube big X, it can be encoded by those a values from all inductive steps. So let's see, so what's the encoding length of those a values? So in each round, so each a value it's an integer not more than 215. So it is a log n bit string. And then because we do log n many rounds of induction, so the total encoding length is log n square. And so this means so the different polynomials we construct is only into the O log n. Okay, so this is how we change. This is our change to this Alman-Williams proof. So it works for our setting.
So I guess it's a clarification question. So log n many rounds means that you're picking like log n many A's, capital A's?
Yeah, so because so in this induction, so every round we move from maybe n bits to m over 2 bits. So and in this until 2.5 setting, so we start with until 2.5 bits. So this induction is in total it takes O log n rounds. And in each round, so we hardcode a value, and each a value is log n length. So this gives the total length of log square. And because our polynomial construction, it only depends on those a values, so we no longer need to look at the whole description of this sub-cube X. So this encoding length gives the bound on different polynomials. Okay, so now let's summarize. So what we talked about today. So our result is we prove the lower bound that e to the p cannot be computed by into the 2.5 size threshold circuit. And our proof is just by designing a circuit analysis algorithm for into 2.5 size threshold circuits. So this improves the previous lower bound of n to the square minus epsilon. And the new ideas behind our proof. So first is that we combine the random restriction technique with the algorithmic method framework. And also there are some remaining issues. So how we solve this is that this approximation polynomial idea. So we use a very small list of approximation polynomials, say into the 10 log n many, to cover all our cases. So they are 2 to the n minus into the epsilon over 10 many columns, but they can be covered by only into the 10 log n many different polynomials. And some remaining over problems. So okay, so first obviously, so how can we push for the circuit lower bounds? So what's the next step in threshold circuit lower bounds, or also for general circuit lower bounds? And another more problem. So for this approximation polynomial technique, so can we find some other applications for this? Okay, so this is the end of my talk today. So does people have any questions?
Yeah, thank you, John. Very great talk. Let me stop the recording and then we can